Hello everyone, this is Niharika, roll number 61. My topic is recognition based on decision theoretic methods and matching, where recognition is the process of identifying an object or a feature in an image or video. It is used in many applications like defect detection, medical imaging, and security surveillance. The basic concept in recognition in decision theoretic applications is the idea of pattern matching based on measures of distance between pattern vectors, where it includes decision functions and decision boundaries. That is, decision function is the property of class belongs to omega I. That is, pattern class is a family of patterns that share some common properties. Each pattern class are denoted by omega 1, omega 2 and so on. Decision boundaries. It is the division of class omega I from omega j. That is, the difference between two classes is equals to 0. The principal objective of this discussion is to develop various approaches for finding decision functions that satisfy the equation. Matching and minimum distance classifier. Well, matching is an important concept in computer vision and object recognition. Images of the same item can be taken from any angle with any lighting and scale. It is a powerful method for matching geometric information in stereo images. It represents each class by a prototype pattern vector. The simplest approach is the minimum distance classifier. The minimum distance classifier is used to classify unknown image data to classes which minimize the distance between the image data and the class in multi-feature space. This defines the prototype class to be the main vector of the patterns of that class. That is mj is equals to, that is pattern class is equals to 1 by pattern class sigma x, where x belongs to a pattern class. We then assign x to class omega if di of x is the smallest distance, that is dj of x is equals to x minus mj. Selecting the smallest distance is equivalent to evaluating the functions using the equation given below. The decision boundary between class omega and class omega j for minimum distance classifier is dij of x is equals to 0. Here the figure is an example taken from an iris flower. The figure shows the decision boundary of minimum distance classifier for the classes of iris versicolor and iris setosa. The dark dot and the squares are the means of the width and the length. Here the circle denotes are the iris setosa and the rectangle here are the iris versicolor. Here horizontal line defines for petal length, that is iris petal length, and the x2 defines for the petal width. Here it is another example given, American Bankers Association. That is, here each number denotes an corresponding waveform according to the character set given below, that is 0, 1, 2, 3 and so on 9. Matching by correlation. Correlation is a mathematical technique to see how close two things are related. The correlation between two images is given as disadvantage and resolve, that is sensitive to change in the amplitude of f and w, performing matching via the correlation coefficient. The general process of correlation is the loading two images and extract their pixel by pixel information, normalize and downsample the pixel information, calculate cross correlation using the processed pixel information, generate visual summaries of cross correlation highlighting areas of maximum image overlap. This is the equation used for correlation, that is C of x comma y is equals to sigma as t f of s comma t of w of x plus s comma y plus t. Here is the arrangement for obtaining the correlation of f and omega at point x0, y0. That is the here the it is an x and it is y. The coordinates of these two denote the correlation here. Here it is an image which denotes the correlation. Coming to optimum statistical classifiers. A probabilistic approach to recognition. If the pattern classifier decides that x came from omega j when it actually came from omega I, it incurs a loss denoted by Lij. That is the equation Rj of x is equals to sigma k is equals to 1 to omega Lkj p of omega k by x. The classifier that minimizes the total average loss is called base classifier. Thus, the base classifier assigns an unknown pattern x to class omega I if r of k is less than r of x. For j is equals to 1, 2 and so on. In other words, x is assigned to class omega I. If omega k is equals to 1 to w lki p of x by omega k into p of w k is less than of p of sigma of q is equals to 1 to w lqj p of x by wq into p of omega q. Base classifier for Gaussian pattern classes. It is the equation used for base classifier, and the base decision function for class omega j is dj of x is equals to p of x by omega j into p of omega j. That is dj of x is equals to log p of omega j plus x power t c power inverse 1 m exponential j minus 1 by 2 into m power t exponential j into c power minus 1 mj. Here it is the probability density functions for two 1D pattern classes. The point x shown is the x not shown is the decision boundary if the two classes are likely to occur. Here m2 is the peak point of one density and the m1 is the peak point of another distance. But the combination of these two is known as the x naught. It is the where two classes are combined each other. Here the figure shows the simple pattern classes and their Bayes decision boundary shown shaded. Here the x1, x2 and x3 are the three coordinates in a simple pattern. The shaded region is the Bayes decision boundary. Here it is the formation of a pattern vector from registered pixels of 4 digital images generated by a multispectral scanner. Here these are 4 multispectral scanner bands and the vector obtained from these bands are x1, x2, x3 and x4. Here it is another example for Bayes. First image is the multispectral and the second is a printout of machine classification results using a Bayes classifier. Thank you.